Welcome to our discussion today. We're going to explore a persistent challenge in industry. Why do good, highly skilled technicians still occasionally install failures? This isn't about a lack of effort. It's about the systems that surround the work. We'll be looking at error-likely tasks, work quality, and how to use hold points and verification to protect our assets and our people. Let's start with a real-world scenario. Imagine a critical pump overhaul where the alignment was technically perfect, yet the equipment failed because it was aligned to the wrong spacer stack. Two visually identical parts were in the same kit. The paperwork was outdated, and a shift change at midnight broke the continuity. This reminds us that precision workmanship cannot save a job if the configuration, information, or verification process is flawed from the start. Why does this matter so much? From a seasoned practitioner's view, we must accept that competence is not immunity. Even the most experienced people face lapses and time pressure. A strong system doesn't just rely on skill. It makes the right action easier to take under pressure. We need to stop blaming technicians, which only hides the evidence, and start building work packs that shape better behavior and independent verification that catches slips before they become failures. By the end of this session, you should be able to recognize the factors that influence performance and identify error-likely steps before the tools even touch the machine. We'll cover how to design better instructions, use peer checks and hold points effectively, and most importantly, how to learn from deviations without simply defaulting to retraining as a solution. Our first step is to see the risk clearly. We need to stop viewing error as a personal failing and start treating it as a system property, one that is influenced by the task, the equipment, the environment, and the organization itself. Before we can solve the problem, we need to speak the same language. We distinguish between a slip, an unintended action during a familiar task, and a mistake, which is an intended action based on a wrong plan. We also look at violations shaped by pressure and performance-influencing factors, or PFs. Understanding these definitions helps us move toward solutions like independent verification and robust post-maintenance testing. The stakes are high because the loss from a maintenance error is always larger than the invoice. Beyond just rework costs, we're talking about process safety risks, early life failures that destroy reliability, and a culture of blame that suppresses the very reporting we need to stay safe. Reliability decisions move safety, capacity, and reputation together. It's important to realize that failure usually develops through a chain of events, not a single act. It starts with a poorly designed task, moves through degrading conditions like poor lighting or time pressure, leads to an error, and finally slips past a weak check. If a single person has to remember every detail correctly for the equipment to work, your system has already spent its safety margin. Warning signs often appear before an event occurs. We see them in workarounds where technicians adapt to unworkable procedures, in interruptions during critical steps, or in set point drift, where units are misread. Even leaving a rag or tool inside a machine is a symptom of a system that isn't managing configuration and closeout effectively. To see if your current system is truly robust, ask these 8 questions. Don't answer with what you intend to do, but with what evidence shows. Are your critical tasks formally identified? Do your job plans show hold points at the point of use? Is your post-maintenance testing covering actual functions? These questions expose the gaps between our procedures and our reality. Now that we've identified the risks, let's move to Section 2, building the operating model. Our goal is to design a maintenance process that is error-tolerant from the initial screening all the way through to functional testing. We follow 5 core principles to keep the system practical. We design for error by assuming people are fallible. We control the configuration so the correct state is unambiguous. We pause at critical steps. We test the function, not just the task. And we learn without blame to preserve evidence for the future. This brings us to the SAFE 6 framework. It's a 6-step control process. Screen the risk, author the work, prepare the conditions, brief and execute, verify criticals, and finally, test and learn. The objective isn't to achieve zero human fallibility. That's impossible. But to reduce error opportunities and strengthen our detection. Step 1 is screening risk. Planners and engineers must break tasks into decisions and actions to identify where an omission or a setting error could happen. By assessing how severe the consequences are and how likely we are to detect an error, we can select the right level of control before work begins. Step 2 is authoring work. This is about making the correct execution crystal clear at the point of use. This means using current drawings, placing warnings before the critical step, and including photos and measurable criteria. A validated work instruction is the essential output here. Step 3 is preparing conditions. Before a job is marked as ready, we must verify the parts, tools, and the workplace. This includes checking part revisions, ensuring tools are calibrated, and assessing factors like lighting and workload. We want to ensure that when the technician starts, they aren't fighting the environment. Step 4 is briefing and executing. The work leader must align the team, discussing potential error traps and confirming that everyone has the authority to stop work if something feels wrong. During execution, the team must follow the sequence and pause if conditions differ from the plan. Step 5 is verifying criticals. For high-consequence attributes, we need a qualified second set of eyes. Whether it's a peer check or a formal independent verification, we must record specific data like torque and clearance before the components are concealed by reassembly. Finally, step 6 is test and learn. We must prove that the affected functions and safeguards actually work by comparing results against acceptance criteria. This is also the time to capture near misses and update our plans so we don't repeat the same mistakes in the next cycle. To make this model work, we need clear decision rules so that convenience doesn't become policy. For example, if a job condition differs from the plan, the rule is to stop and obtain a technical disposition. If two parts look similar, the rule is to physically segregate them. These rules provide the evidence required to close out a task safely. With the model in place, Section 3 focuses on making it executable. We need to give our planners, supervisors, and technicians clear controls and evidence requirements that they can actually use in the field. Reliability often fails in the gaps between departments. By naming one accountable owner for each stage, from the planner authoring the instructions to the technician recording evidence and the operator making the final return of service decision, we ensure that nothing falls through the cracks. Standard work is what turns our good intentions into repeatable execution. By following this 7-step flow of analyzing, authoring, preparing, briefing, executing, verifying, and testing, we ensure that every critical state of the equipment is proven before we walk away. We must remember that a control is not just a general procedure. It's a specific, observable action. Whether it's an error-likely task analysis, revision control on a drawing, or form material accounting, each control must have a defined verification method and a clear owner. Data collection should be purposeful. We only want to capture the minimum data that could change a decision. This includes configuration details, as-found states, critical attributes like alignment, and any deviations. This allows a second person to reconstruct exactly what was done and tested. To manage this, we use measures that trigger action rather than just admiration. We track leading indicators like work pack defects and critical check compliance alongside lagging indicators like rework rates and early life failures. This gives us a true picture of our maintenance quality. A durable culture is built through a management cadence. This includes pre-job briefs, hold point verifications, and weekly reviews of rework and deviations. By escalating exceptions through a regular rhythm, we improve the system without needing a meeting for every single issue. Technology can help, but only if it reinforces the discipline we've already defined. Mobile work packages, electronic hold points, and tool tracking are powerful tools for ensuring that the most current information and the required evidence are captured right at the task. In our final section, we'll look at how to apply, verify, and sustain these methods. We'll revisit our case study and look at a 90-day roadmap for reducing errors in your plant. Recall our pump overhaul case. The team was faced with similar parts, a superseded drawing, and a midnight shift change. In that moment, the decision point is critical. Do you close the job, or do you stop and inspect the records? Without a system, they chose to close it, and the error remained hidden. If we apply the Safe 6 framework to that same case, the intervention changes the system. We screen for the risk of similar parts, we issue the current drawing with a warning, we segregate the parts, and we mandate an independent verification of the spacer before the guard is closed. We transform a likely failure into a detected and corrected task. Success becomes visible through specific indicators. The correct configuration is confirmed, the handover is structured, and the alignment is tied to actual part identity. The key lessons are that precision cannot rescue the wrong configuration, and critical checks must happen before concealment. Now, let's try a tabletop exercise. Imagine replacing a safety instrument where units could be entered in kPa or bar. Where could the mistakes occur? Which factors increase the risk on this specific shift? Identifying these error traps now is what prevents a disaster during the day shift loop test. As you implement this, watch out for common traps. Don't stop at technician error or rely solely on retraining. Avoid the urge to put an independent check on everything. Target the high consequence attributes instead. And remember, punishing near-miss reporting is the fastest way to kill your learning culture. A 90-day roadmap helps you build evidence before scaling. Spend the first 30 days baselining your top tasks. The next 30 days piloting a redesign job with targeted hold points. And the final 30 days verifying outcomes and scaling to the next family of tasks. When talking to management, build a business case based on value. The costs of task analysis and verification are offset by the massive savings from less rework, fewer startup defects, and reduced process safety exposure. Reliability is a high-return investment. To ensure the system is working, use this 12-point field audit. Score only what you can actually observe or trace. Are the drawings at the point of use? Are parts positively identified? This turns a vague feeling about quality into a measurable reality. In summary, remember that competence does not eliminate fallibility. Good technicians need a system that anticipates error. As leaders, we should commit to 3 things. No critical step without a control, no hidden attribute without verification, and no handback without functional evidence. For those who want to dive deeper, we've provided a list of selected articles, standards, and case studies. These resources cover everything from managing human failures to specific investigations into maintenance material left in equipment. I'd like to acknowledge the sources of the industrial photography used throughout this presentation. These real-world images help ground our discussion in the actual environments where our technicians work every day. I'll leave you with one final question. Which good technician is your system currently asking to be the last barrier? Let's move our error controls upstream before workmanship becomes our only defense. Thank you for your time today.